June 19, 1918, Pikes Peak, Colorado. A Packard truck ground its way up 23 miles of unpaved mountain road, carrying a cargo that would change aerial warfare forever. Lashed to the truck bed was a Liberty V-12 aircraft engine, all 350 horsepower of it connected to a massive propeller and a strange metal device that looked like a Nautilus shell made of steel. At 14,115 feet above sea level, where the air was so thin that most men struggled to breathe, Dr. Sanford Alexander Moss prepared to prove that altitude was no longer aviation's enemy. Preparing and narrating this type of story took us long efforts and hard work. So, if you are enjoying the story, please consider subscribing to our channel. The Liberty engine, unassisted, could barely produce 230 horsepower at this altitude. That represented a catastrophic 35% loss of power, the kind of deficit that made high-altitude flight not just difficult, but strategically impossible. But Moss wasn't here to accept impossibility. He was here to shatter it. His turbosupercharger, drawing energy from exhaust gases most engineers considered waste, would force-feed compressed air back into the engine's cylinders, tricking them into believing they were still at sea level. When the engine roared to life, and the instruments climbed toward 356 horsepower, nearly matching sea-level performance at an altitude where engines were supposed to choke and die, Moss and his small team from General Electric knew they had just solved one of aviation's most fundamental problems. 26 years later, formations of Boeing B-17 flying fortresses would cruise at 25,000 feet over Nazi Germany, staying above the worst of the anti-aircraft fire, delivering strategic bombing that would help break the Third Reich's industrial capacity. And every single one of those bombers would carry 4 General Electric turbosuperchargers, descendants of the device Moss had tested on that Colorado mountaintop. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This is the story of how one engineer's determination to harness wasted energy revolutionized military aviation, how a device most experts dismissed as too complex for military use became the technological foundation of America's strategic bombing campaign, and how the ability to fight at 30,000 feet helped the Allies win World War II. The journey to Pikes Peak began not in wartime urgency, but in peacetime curiosity. Born August 23, 1872, in San Francisco, California, to Ernest Goodman Moss and Josephine Sanford, young Sanford showed an early fascination with mechanical systems and thermodynamics that would define his entire career. At 16 years old, while working as a $4 per week mechanic in a shop producing compressed air machinery, Moss had an insight that would echo through decades. If fuel could be burned in compressed air, he reasoned, the energy output would increase tremendously. This wasn't just a passing thought. This was the seed of an obsession. Moss took that idea with him to the University of California, where he earned his bachelor's and master's degrees in engineering. His master's thesis proposed replacing locomotive piston engines with smoother gas turbines, an idea decades ahead of its time. But Moss wasn't content with imagination. He needed to prove his concepts worked. In 1903, he earned his doctorate from Cornell University, where his dissertation titled The Gas Turbine, an Internal Combustion Prime Mover, caught the attention of engineers at General Electric. The company hired him immediately, bringing him to their steam turbine department in Lynn, Massachusetts, where he would work alongside legendary figures like Elihu Thomson, Edwin W. Rice, and Charles Steinmetz. At GE, Moss found himself in the company of brilliant minds and cutting-edge industrial research, but he also found frustration. His gas turbine concepts were theoretically sound but practically impossible with the materials and manufacturing techniques of the early 20th century. The metals couldn't withstand the temperatures. The compressors weren't efficient enough. Every test ended in failure or marginal performance that couldn't justify commercial development. For 15 years, Moss worked on steam turbines and centrifugal compressors for industrial applications, refining his understanding of fluid dynamics and thermodynamics, while his dream of the gas turbine remained tantalizingly out of reach. Then came World War I, and with it, an entirely new set of engineering challenges. Aircraft had barely existed a decade earlier when the Wright brothers made their historic first flight at Kitty Hawk in 1903. Now, in 1917 and 1918, airplanes had become weapons of war, and the major powers were discovering that whoever controlled the skies gained tremendous tactical and strategic advantages. Scout planes spotted enemy movements, fighter planes attacked ground targets, and battled each other for air superiority. And bomber aircraft, still primitive but growing in capability, struck behind enemy lines at supply depots, rail yards, and industrial facilities. But every aircraft faced the same fundamental limitation that had plagued aviation since the beginning. As altitude increased, engine power decreased catastrophically. The reason was simple physics. At sea level, atmospheric pressure was approximately 29.92 inches of mercury, and the air contained enough oxygen to support robust combustion in aircraft engines. At 10,000 feet, atmospheric pressure dropped to about 20.58 inches of mercury, a 30% decrease, and engines lost power proportionally. At 15,000 feet, the altitude where German fighters were operating with growing effectiveness, American and Allied pilots found their engines gasping for air, producing perhaps half their rated horsepower, making their aircraft sluggish, unresponsive, and dangerously vulnerable. German aircraft engine builders at BMW, Maybach, and Mercedes had responded to this challenge by building fighter plane engines with monstrous piston displacements and high compression ratios to offset the losses from breathing thinner air at altitude. These engines employed 3 throttle levers that had to be opened progressively to keep the engine from imploding at sea level, and they successfully climbed to 20,000 feet. In France, engineer Auguste Rateau had turbocharged a Renault aircraft engine toward the same end, using exhaust gases to drive a compressor. But Rateau's design suffered persistent failures from excessive heat, and French testing had not yet produced a reliable system. The United States Army Air Service, meanwhile, was desperately trying to catch up. America had entered the war in April 1917, nearly 3 years after it began, and while the nation had industrial capacity and growing numbers of trained pilots, it lacked advanced aviation technology. The Liberty engine, a 12-cylinder design hastily created through a remarkable collaboration between Packard Motor Car Company and Hall Scott Motor Company, had become the standard American aircraft power plant. When the government contracted manufacturing to multiple automotive companies, it represented an extraordinary feat of rapid industrial mobilization. But the Liberty, like every other piston engine of the era, suffered catastrophic power loss at altitude. In autumn 1917, William F. Durand, director of the National Advisory Committee for Aeronautics, the predecessor organization to NASA, received incomplete reports that a French engineer named Auguste Rateau was attempting to develop engines for high altitudes using a turbo-driven air compressor. Durand, a Cornell graduate himself, remembered a student from 2 decades earlier who had worked on gas-driven turbo engines. He remembered Sanford Moss. Durand wrote to Edwin W. Rice, president of General Electric, requesting Moss's services for what would become a matter of national urgency. His letter, dated late 1917, laid out the challenge with stark clarity. At the present time, in connection with the development of the airplane and the Liberty engine for driving same, there is no problem which is perhaps more seriously before the government officials than that of maintaining at high altitudes the power of the engine. In this connection, we are especially desirous of developing the possibilities of a pre-compression of the air before going to the engine carburetor, thus maintaining, as nearly as may be, constant conditions regarding pressure at all altitudes. Rice understood what Durand was asking. The government needed General Electric's expertise in turbines and compressors applied to the most critical bottleneck in military aviation. And Rice knew that Sanford Moss, despite 15 years of frustrated gas turbine development, had exactly the knowledge and skills required to solve this problem. Moss was authorized to begin development immediately, working with extraordinary urgency. The war was consuming lives at a terrifying rate on the Western Front, and if American air power was going to make a meaningful contribution before the conflict ended, solutions needed to come quickly. Moss and his team at GE's Lynn facility worked with remarkable speed. They had access to engineering drawings of Rateau's experimental device, but Moss's team had their own ideas based on years of industrial turbine and compressor experience. By June 1918, just months after beginning serious development work, General Electric's Lynn steam turbine department shipped a prototype turbosupercharger to the War Department's Airplane Engineering Division at McCook Field in Dayton, Ohio, for adaptation to a Liberty 12 aircraft engine. The device Moss had created was ingenious in its elegant simplicity. His design used a small turbine wheel, driven by exhaust gases that normally represented pure waste heat, to turn a supercharger compressor. The turbine wheel was connected by a shaft to a centrifugal compressor impeller. The piston engine's hot exhaust gas was directed into the device's turbine, spinning it at extraordinary speeds, tens of thousands of revolutions per minute. The fast-rotating impeller squeezed the thin air fed into the compressor, creating higher air density and oxygen levels closer to sea-level pressure. This turbo-supercharged air was then fed into the piston engine's carburetor, dramatically increasing the amount of fuel-air mixture that could be burned, and therefore the power the engine could produce. The innovation that made Moss's design work where others had failed was cooling. Previous attempts at turbo-supercharging had foundered on the problem of excessive heat. The turbine wheel, spinning at tremendous speeds and exposed to exhaust gases that could exceed 1,000 degrees Fahrenheit, would quickly fail from thermal stress. Moss incorporated passages for critical cooling air to flow around the turbine wheel, managing temperatures enough to prevent catastrophic failure. He later joked that the device kidded the piston engine to think it was at sea level, but that simple phrase understated the profound engineering achievement his team had accomplished. Initial testing at McCook Field in Dayton demonstrated that the turbo-supercharger was operative and could boost engine power, but it also revealed a significant problem. At McCook Field's relatively low altitude, approximately 750 feet above sea level, atmospheric pressure was still high enough that even modest supercharging caused serious preignition in the Liberty engine. Preignition occurred when the fuel-air mixture ignited before the spark plug fired, creating destructive detonation that could burn or break engine components within seconds. The engine would develop 470 horsepower at 1700 RPM with the supercharger active, compared to the Liberty's standard 420 horsepower, but spark plugs failed almost immediately, and numerous other difficulties developed. Testing at sea-level atmospheric pressure was simply pushing the engine beyond its design limits. The paradox was clear. The turbo-supercharger worked too well at low altitude, causing problems. But it was specifically designed to solve high-altitude problems. To properly test the device, Moss needed to operate it where it was actually supposed to work in thin air, at significant altitude, where the compressed air wouldn't overwhelm the engine's combustion limits. Moss could have requested test flights with experimental aircraft, risking pilots' lives with unproven equipment. Instead, he had a better idea that was both safer and more scientifically rigorous. He would build a mobile laboratory, mount the entire test apparatus on a truck, and drive it to the top of a mountain where the thin air would allow proper evaluation of the turbo-supercharger's performance. It was brilliantly pragmatic, no risk to test pilots, complete control over test conditions, and the ability to make adjustments and repairs on site rather than waiting for an aircraft to land between test runs. The question was, which mountain? Moss needed a peak high enough to provide meaningful altitude at least 12 to 14,000 feet, but accessible enough that a heavy truck could reach the summit. In 1918, there weren't many options. Pikes Peak in Colorado, rising to 14,115 feet and featuring an auto highway that had been completed in 1915, was the obvious choice. The road was unpaved, challenging, and dangerous, with steep grades and sharp switchbacks carved into the mountainside, but it was passable for a heavy vehicle if driven carefully. Together with McCook Field engineer C.P. Grimes and a small crew of technicians, Moss assembled his mobile laboratory. The turbocharged Liberty engine was mounted on a heavy dynamometer test stand to measure torque and power output precisely. A massive four-blade propeller was attached to absorb the engine's power without a propeller, creating resistance. The engine would overspin and destroy itself. Various support systems for fuel, cooling, and instrumentation were integrated into the assembly. The entire contraption, looking like something between a carnival ride and an industrial accident, was bolted securely to a Packard motor truck. After a month of preparation in Dayton and a week-long 1,300-mile train ride, the mobile laboratory arrived in Colorado Springs on September 10, 1918. The crew fired up the Packard truck, which chugged its way up the Pikes Peak auto highway, carrying several tons of experimental equipment up switchbacks, where a single mistake would send truck, engine, and men tumbling down the mountainside. It took hours of careful driving, the Packard's transmission grinding through low gears, the crew occasionally needing to stop and let the truck's own engine cool before continuing the ascent. At the summit, on a rocky flat approximately 300 feet in diameter, Moss and his team finally prepared for the tests that would determine whether months of development work had produced a functional solution or an expensive failure. The setting was dramatic. The massive peaks of the Rocky Mountains stretched in every direction, their slopes already showing the first snow of the approaching winter. The Great Plains spread out far below, visible for hundreds of miles on clear days. The air was thin enough that simply walking required effort, and any strenuous work left men gasping. September 10, 1918, was the day Moss had been working toward for months, the culmination of 15 years of expertise in turbines and compressors, and potentially the solution to one of military aviation's most critical problems. As the sun rose over the Colorado high country, the team positioned the mobile laboratory, checked all connections and instrumentation, and prepared to discover whether Sanford Moss's turbosupercharger would work as theory predicted, or fail like so many ambitious engineering concepts before it. The tests would run for 4 weeks, with the team making approximately 25 individual runs under varying conditions. Each evening, the test rig was carefully covered in canvas to protect it from the elements before the crew drove back down the mountain to rest in Colorado Springs. On several mornings, they returned to find their equipment frozen inside a cocoon of snow, requiring hours of work just to prepare for that day's testing. A small shack on the mountaintop served as repair shop when components failed or adjustments needed to be made. And components did fail. Turbosuperchargers were operating at the edge of what early 20th century materials and manufacturing could achieve. During the test series, Moss's team dealt with clogged carburetor jets that required disassembly and cleaning. Leaks developed in exhaust manifold joints where thermal expansion and contraction stressed connections. A leak in the compressor housing, later attributed to casting flaws in the original manufacturing, required sealing. 2 thrust washers made of highly hardened steel broke under the extreme stresses, forcing Moss to redesign them using bronze, which performed much better. Several exhaust manifold bolts failed and needed replacement, but these were mechanical problems with straightforward solutions. The fundamental question was whether the turbosupercharger could restore engine power at altitude, and on that critical measure, Moss's design succeeded beyond what even he had hoped. Baseline sea level tests, conducted at McCook Field before the expedition had established that the Liberty engine produced a maximum of 354 horsepower at 1800 RPM at 29.92 inches of mercury atmospheric pressure. These were the numbers Moss needed to match at 14,000 feet if his turbosupercharger was going to prove its value. On Pikes Peak summit, with the turbosupercharger shut down and the Liberty engine running naturally aspirated, breathing the thin mountain air without assistance, the best the team could achieve was 230 horsepower. That represented a devastating power loss of over 35%, exactly the kind of deficit that made high-altitude flight so problematic. Aircraft operating at this altitude would be slow, sluggish, and unable to climb higher or maneuver effectively. With the turbosupercharger in operation, the nozzle boxes glowing bright red from exhaust heat, the turbine wheel screaming at tens of thousands of revolutions per minute, and the Liberty engine on the ragged edge of detonation, Moss measured a maximum horsepower of 377, better than they had achieved at sea level. For brief periods, with the supercharger forcing compressed air into the cylinders, the engine at 14,000 feet was actually outperforming its sea level rating. The turbosupercharger was giving the engine over 147 additional horsepower compared to naturally aspirated operation at altitude. There were limitations. In his notes from the test series, Moss conceded that the 377 figure could be held for only 30 seconds before spark plugs failed from the extreme combustion pressures and temperatures. But the turbocharged Liberty also withstood a 4-hour endurance run at 313 horsepower, 83 horsepower, more than naturally aspirated performance at altitude, and close enough to sea-level power to represent transformative capability for high-altitude flight. The mathematics were undeniable. At 14,000 feet, the turbosupercharger increased power output by over 50% compared to naturally aspirated operation. That kind of performance advantage would allow aircraft to fly higher, faster, and with greater payload capacity than opponents lacking the technology. Moss left no record in his notes of any celebrations the team may have held after successfully completing the test series and driving back down the mountain, but everyone involved certainly deserved one. They had just proven that altitude was no longer an insurmountable barrier to aircraft performance. The problem was timing. By the time Moss completed his Pikes Peak tests in October 1918 and filed his report with the Army Air Service, World War I was entering its final weeks. The armistice was signed November 11, 1918, ending the war before turbosuperchargers could be manufactured in quantity and installed in operational aircraft. The technology had arrived too late to affect the conflict that had driven its development. But the men who understood aviation's future recognized immediately what Moss had accomplished. After ongoing development and refinement through 1919 and 1920, Moss installed a turbo-supercharged Liberty engine in a Lepaire biplane, a two-seat reconnaissance aircraft that normally had an operational ceiling around 15 to 20,000 feet. On July 12, 1919, the modified Lepaire took off for the first time and demonstrated truly remarkable performance. The aircraft achieved 137 miles per hour at 18,400 feet, compared to 90 miles per hour at the same altitude without a supercharger. That represented a 52% increase in speed, transforming the aircraft's capability. More dramatically, in 1921, a turbo-supercharged Lepaire biplane piloted by U.S. Army aviators set a new world altitude record by reaching over 40,000 feet, more than double what a naturally aspirated Lepaire could achieve, and higher than any human being had ever flown before. The record demonstrated conclusively that turbo-supercharging wasn't just a marginal improvement. It represented a fundamental expansion of aviation's operational envelope. Newspapers around the world heralded the achievement, and within aviation circles, Sanford Moss became recognized as the man who had solved altitude's tyranny over aircraft performance. But Moss himself was characteristically modest about the achievement. He was an engineer, not a publicity seeker. He understood that the turbo-supercharger was one element in aviation's evolution, and that countless other innovations would be required before aircraft reached their full potential. Through the 1920s and 1930s, turbo-supercharger technology continued to develop. General Electric maintained its expertise, producing improved designs with better efficiency, greater reliability, and easier maintenance. By the mid-1930s, turbocharged engines were being installed in racing cars. At least one Indianapolis 500 winning car was fitted with a Moss turbo-supercharger, demonstrating the technology's versatility. More importantly for military aviation, the technology was maturing to the point where it could be reliably manufactured at scale and integrated into operational aircraft. In 1937, as Adolf Hitler's power grew in Germany and war clouds gathered over Europe, General Electric received a large order from the United States Army Air Corps to build turbo-superchargers for the new generation of American military aircraft then entering development. The order specified turbo-superchargers for Boeing B-17, Flying Fortress heavy bombers, Consolidated B-24 Liberator heavy bombers, Lockheed P-38 Lightning twin-engine fighters, and Republic P-47 Thunderbolt single-engine fighters. The Army Air Corps, studying lessons from the Spanish Civil War and observing German rearmament, understood that the next war would be fought at altitudes that required turbo-supercharging to maintain competitive performance. The order was massive enough that GE established a dedicated supercharger division in Lynn, Massachusetts, with manufacturing facilities designed specifically for high-volume production of these complex devices. Sanford Moss, who had retired from General Electric in 1938 at age 65, after receiving the Collier Trophy, one of aviation's highest honors for his work on the turbo-supercharger, was brought back as a technical advisor. At 69 years old, he returned to work, refining the technology he had pioneered 2 decades earlier, driven by the knowledge that war was coming and American aviators would need every technological advantage they could get. The Boeing B-17 Flying Fortress, first flown in 1935 as the Model 299 prototype, had been designed from the outset as a strategic heavy bomber capable of carrying significant bomb loads deep into enemy territory at altitudes above 20,000 feet. The aircraft that emerged from Boeing's Seattle facilities was technologically advanced for its era, featuring all-metal construction, 4 engines, and defensive armament that would eventually justify its Flying Fortress nickname. But the feature that made sustained high-altitude flight possible was less visible and less celebrated than the guns and bombs. It was the 4 General Electric turbo-superchargers, one for each Wright-R 1820 Cyclone radial engine, that allowed the B-17 to climb to 30,000 feet and maintain cruise speed while carrying thousands of pounds of bombs. Early B-17 variants, the original 13Y B-17 seconds, delivered in 1937, had demonstrated the basic soundness of Boeing's design, but they lacked turbo-superchargers and had operational ceilings limited to around 25,000 feet. When testing was completed on an experimental aircraft designated Y-1B-17 Amperes, which had been equipped with turbo-superchargers in a ventral nacelle mounting configuration beneath each engine, the results were dramatic. The turbo-supercharged B-17 Amperes achieved a service ceiling of 38,000 feet, a considerable jump over naturally aspirated versions, and a top speed of 271 miles per hour at 25,000 feet. The turbochargers worked, and they transformed the B-17's high-altitude capability. The initial mounting configuration, with turbo-superchargers beneath the nacelles, quickly proved aerodynamically problematic, creating turbulence and drag. Engineers redesigned the installation, relocating the turbo-superchargers to positions outboard of engines 1 and 4 and inboard of engines 2 and 3, with exhaust tubing routed around the landing gear wells. Engine air intakes and intercooler intakes were repositioned on the wing's leading edge. The redesign added weight turbosuperchargers, ducting, intercoolers, and associated systems contributed approximately 310 pounds per engine and over 1,200 pounds total, but the performance advantages more than justified the weight penalty. The B-17's turbo-supercharged Wright-R 182097 Cyclone engines, each producing 1,200 horsepower, gave the aircraft capabilities that would prove decisive in the strategic bombing campaign over Europe. The bomber could cruise at altitudes between 25,000 and 35,000 feet, depending on bomb load, putting it above the worst of German anti-aircraft artillery and forcing Luftwaffe fighters to climb to their operational limits to engage the formations. The service ceiling of 35,600 feet meant B-17 seconds could, when necessary, climb even higher to avoid weather or threats. This high-altitude capability was central to American strategic bombing doctrine. The United States Army Air Forces, unlike the Royal Air Force, which had shifted to nighttime area bombing after suffering heavy losses in daylight raids, remained committed to precision daylight bombing using the Norden bombsight. The theory was that American bombers, flying in tight defensive formations at high altitude, where German fighters struggled to operate effectively, could strike specific industrial and military targets with accuracy sufficient to cripple Nazi Germany's war production without the indiscriminate destruction of nighttime area bombing. The theory was only partially validated in practice weather over northern Europe, often obscured targets. The Norden bomb site's accuracy was overstated, and German fighter defenses proved more lethal than predicted. But the commitment to daylight precision bombing shaped how America fought the air war over Europe. And that commitment was only possible because turbosuperchargers gave B-17 seconds and other American bombers the ability to operate at altitudes where they had at least some protection from anti-aircraft fire. The reality of strategic bombing over Nazi Germany was far more brutal than pre-war theorists had imagined. When the 8th Air Force began operations from England in 1942, flying B-17 seconds on missions deep into German-occupied Europe, the crews discovered that their flying fortresses were indeed tough and survivable, but they were not invulnerable. German fighter pilots, flying Messerschmitt Bf 109 seconds and Focke-Wulf 4 190 seconds, developed tactics specifically designed to break up bomber formations and pick off isolated aircraft. Anti-aircraft artillery, though less effective at extreme altitude, could still reach formations flying at 25,000 feet and create lethal curtains of exploding steel. The losses were staggering. In early 1943, when the first American raid into Germany proper targeted the railroad marshalling yards at Hamm, crews discovered just how determined German defenses would be. By autumn 1943, the 8th Air Force was losing bombers at an average rate of approximately 5% per mission. The mathematics were grimly simple. A bomber crew was required to complete 25 missions to finish their tour of duty. With a 5% loss rate per mission, the cumulative probability of survival through 25 missions was approximately 1 in 3. 2/3 of bomber crews could expect to be killed, severely wounded, or taken prisoner before completing their tour. The worst single mission came on October 14, 1943, when 291 B-17 seconds and B-24 seconds attacked the ball-bearing factories at Schweinfurt, Germany, in an operation that became known as Black Thursday. The bombers flew deep into Germany without fighter escort. American fighter aircraft of the time lacked the range to accompany bombers all the way to targets in central Germany and back. Over Schweinfurt, German fighter units swarmed the formations, attacking from every angle, and when the bombers finally turned for home, the fighters pursued them for hours as they struggled back toward England. 60 bombers were shot down. Another 17 were so badly damaged they were scrapped upon return. Over 600 airmen were killed, wounded, or captured on that single mission. The Schweinfurt raid demonstrated that the B-17, for all its defensive armament and rugged construction, could not survive deep penetration missions without fighter escort. The high-altitude capability that turbosuperchargers provided was necessary but not sufficient for survival. The bombers needed escort fighters that could match their range and protect them from German interceptors. Until such fighters became available, deep raids into Germany were suspended. The strategic bombing campaign, the operational concept that had driven so much of American pre-war planning, hung in the balance. But the turbosuperchargers themselves never failed. Through all the missions, through all the combat damage and mechanical stress, the General Electric turbosuperchargers on B-17 engines performed with remarkable reliability. Pilots controlled turbosupercharger boost using a system of manual controls in early aircraft, then later automated systems that maintained desired manifold pressure across different altitudes. The Eclipse regulators and later Minneapolis Honeywell electric control systems used engine oil pressure or electrical actuators to adjust wastegate position, regulating how much exhaust gas flowed through the turbine versus bypassing directly outside. Operating turbosuperchargers required skill and attention. During climb to operational altitude, manifold pressure would actually increase as the differential pressure between exhaust stack back pressure and outside atmospheric pressure increased, spinning the turbo impeller faster and compressing intake air more aggressively. Pilots had to monitor manifold pressure gauges carefully and adjust controls to prevent overboost, which could damage engines. There were occasional mechanical issues. Wastegates could stick shut, creating runaway superchargers that overboost engines and cause them to lean out dangerously. But these were manageable operational challenges, not fundamental design flaws. The turbosupercharger's greatest vulnerability was to battle damage. The turbine wheels could not tolerate any back pressure, which is why they were exposed rather than ducted. A direct hit from flak or cannon fire could destroy a turbosupercharger, and the engine would immediately lose its high-altitude performance capability, forcing the aircraft to descend to lower altitudes, where the crew would face more intense anti-aircraft fire. But this was a vulnerability inherent to any exposed aircraft system. What mattered was that when turbosuperchargers were operating, they gave B-17 seconds the altitude capability that made strategic bombing feasible. February 1944 marked the resumption of deep penetration raids into Germany, but with a critical difference. The North American P-51 Mustang, equipped with Packard-built Rolls-Royce Merlin engines and drop tanks that gave it unprecedented range for a single-engine fighter, began arriving in England in numbers sufficient to escort bomber formations all the way to their targets and back. With P-51 seconds providing protection against German fighters, and with the altitude capability that turbosuperchargers provided keeping them above the worst anti-aircraft fire, B-17 formations finally had both elements required for sustained strategic bombing operations. Through the spring and summer of 1944, as Allied forces prepared for and then executed the D-Day landings in Normandy, heavy bomber formations struck at German oil production facilities, aircraft factories, transportation networks, and other strategic targets. The bombers flew at altitudes between 23,000 and 30,000 feet, typically, sometimes higher when mission requirements or weather demanded. At these altitudes, the thin air that would have choked naturally aspirated engines to perhaps 60% of their rated power was compressed by General Electric turbosuperchargers back to sea-level density, allowing Wright Cyclone engines to produce their full 1,200 horsepower and give B-17 seconds the speed and climb rate they needed to survive. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The strategic impact of high-altitude bombing capability extended beyond individual missions. The German industry, forced to operate under constant threat of attack from bombers that could strike at any time and at altitudes that made defense difficult, suffered disruptions that cascaded through the entire war economy. Fighter aircraft that should have been deployed to the Eastern Front against Soviet forces instead defended German airspace against American and British bombers. Anti-aircraft artillery that could have supported ground forces was instead positioned around industrial facilities. Resources that should have gone to tank and aircraft production were diverted to repair bomb damage and disperse factories. The oil campaign of 1944 demonstrated the cumulative effect of sustained high-altitude strategic bombing. Beginning in May 1944, American heavy bombers systematically attacked synthetic oil production facilities throughout Germany and occupied territories. The Leuna Works, the Politz plant, refineries in Romania all came under repeated attack by formations of B-17 seconds and B-24 seconds, flying at altitudes where German anti-aircraft fire was less accurate and where fighters struggled to operate effectively. By September 1944, German oil production had dropped to less than 30% of pre-campaign levels. Luftwaffe pilots found themselves grounded not because their aircraft were destroyed, but because there wasn't fuel to fly them. Wehrmacht armoured divisions that had terrorized Europe with blitzkrieg tactics discovered that even the most advanced tanks are useless without fuel. None of this would have been possible without turbosuperchargers. The altitude capability they provided was fundamental to the entire strategic bombing campaign. A B-17 without turbosuperchargers was just another medium-altitude bomber, vulnerable to the full range of German defences and unable to carry heavy bomb loads over long distances. A B-17 with turbosuperchargers was a strategic weapon that could strike the heart of Nazi Germany's industrial capacity from bases in England. By war's end, General Electric and Ford Motor Company, which had been brought into turbosupercharger production to meet massive wartime demand, had manufactured over 300,000 turbosuperchargers. Beyond the B-17, turbosuperchargers equipped the B-24 Liberator heavy bomber, the B-29 superfortress that would eventually bomb Japan into submission, the P-38 Lightning twin-engine fighter, and the P-47 Thunderbolt single-engine fighter. Each of these aircraft relied on turbosuperchargers to maintain engine power at the high altitudes where modern aerial warfare was fought. The P-47 Thunderbolt, in particular, demonstrated what turbosupercharging could achieve when applied to a fighter aircraft. Powered by a massive Pratt & Whitney R2800 double Wasp radial engine producing 2,000 horsepower and equipped with a General Electric turbosupercharger, the P-47 could reach altitudes above 40,000 feet and still maintain combat effectiveness. German fighter pilots learned to fear the P-47's ability to dive on them from above with tremendous speed, attack with devastating firepower from 850 caliber machine guns, and then climb back to altitude faster than German fighters could follow. That combat superiority came directly from turbosupercharging. The Japanese, who captured several B-17 seconds early in the war when American forces in the Philippines were overwhelmed, carefully studied the aircraft and recognized the turbosupercharger as one of its most significant technological advantages. Japanese aeronautical engineers, including Mitsubishi engineer Hisanojo Ozawa, were particularly interested in the engine turbosuperchargers, along with the Norden bombsight and automatic flight control systems. Despite shortages of critical materials and manufacturing difficulties, Japan attempted to develop turbosupercharged aircraft, including the Ki-83 and Ki-87, but never achieved the reliability and production scale that characterized American turbosupercharger development. Germany, despite its reputation for advanced engineering and its early dominance in aerial warfare, never successfully deployed turbosupercharged aircraft in significant numbers. German engineers understood the theoretical advantages of turbocharging versus mechanical supercharging, the ability to recover waste heat from exhaust rather than drawing power from the engine crankshaft, but they faced severe technical challenges. High-temperature alloys required for exhaust ducting and turbine blades were in short supply in Germany, as the war progressed and strategic materials became scarce. Reliable control systems that could prevent overspeeding and turbine failure required sophisticated manufacturing capabilities. Mechanical resonance issues caused vibration that led to fatigue failures. Efficient intercoolers needed to be designed if the advantages were to be fully exploited. These were not insurmountable technical problems. American engineers had solved all of them through careful development work, but Germany's war situation prevented the sustained engineering effort required. By the time German industry might have fielded turbo-supercharged fighters in quantity, Allied bombing had disrupted production facilities, strategic materials were unavailable, and the Reich was fighting desperately on multiple fronts. Germany instead relied on mechanically supercharged engines, including sophisticated two-stage superchargers on later versions of the Messerschmitt Bf 109 and Focke-Wulf Fock W190, which provided good high-altitude performance but could never match the efficiency of turbo-supercharging. Britain, America's closest ally, developed excellent mechanically supercharged engines, particularly the Rolls-Royce Merlin, with its two-stage supercharger that powered the Supermarine Spitfire to competitive high-altitude performance. But British engineers recognized the superiority of American turbo-supercharging technology for heavy bombers and fighter aircraft operating at extreme altitudes. The difference was not just theoretical. A two-stage, mechanically driven supercharger consumed perhaps 15% of an engine's power to drive the compressor. A turbo-supercharger, using waste heat that would otherwise be expelled uselessly through the exhaust, consumed almost no engine power. The slight back pressure in the exhaust system was negligible. That meant more power available for propulsion, higher speeds, better climb rates, and superior combat performance. After the war, when analysis could be conducted dispassionately and with access to captured German and Japanese documents, aviation historians and military analysts reached consistent conclusions about the technological factors that contributed to Allied victory in the air war. Strategic factors mattered enormously. American industrial capacity, pilot training programs, and operational doctrine all played critical roles. But among the technological advantages that American and Allied forces enjoyed, turbosupercharging ranked at the very top of the list. It was an enabling technology that made high-altitude strategic bombing feasible, that gave American fighters performance advantages over opponents, and that ultimately helped break the Axis powers' ability to sustain industrial war production. Sanford Moss lived to see the technology he had pioneered 25 years earlier become one of World War II's decisive weapons. During the war, though officially retired, he consulted with General Electric and the Army Air Forces on turbosupercharger production and refinement. He also worked on experimental turbine engines for the Bell XP 59 amperes Era Comet, America's first jet aircraft, bringing his gas turbine expertise full circle after 40 years of development. The XP 59 amperes first flew in October 1942 from Muroc Dry Lake in California, later renamed Edwards Air Force Base, powered by General Electric IA turbojet engines that represented the next evolution in aircraft. Propulsion beyond piston engines and turbosuperchargers. Moss died November 10, 1946, at age 74, in Lynn, Massachusetts, the same city where he had worked for General Electric for over 4 decades. His obituary in technical journals and engineering publications recognized his contributions to aviation, but most Americans who had benefited from his work, the bomber crews who flew at 30,000 feet over Germany, the fighter pilots who climbed to 40,000 feet to intercept enemy aircraft, the millions of civilians whose freedom was secured by Allied victory, never knew his name or understood how his engineering genius had shaped the war's outcome. In 1940, before America entered World War II, Moss had been awarded the Collier Trophy, presented by the National Aeronautic Association, for his development of the turbosupercharger. The award recognized that his work had fundamentally changed aviation's possibilities. In 1953, on the 50th anniversary of powered flight, Air Force Lieutenant General James Doolittle, the same James Doolittle who had led the daring 1942 raid on Tokyo, and later commanded the 8th Air Force in Europe, placed a monument at the top of Pikes Peak commemorating Moss's 1918 tests. The monument's inscription noted that Moss's achievements had been instrumental to high-altitude aviation and had helped win World War II. The scientific and engineering principles that Moss had applied were not new. Auguste Rateau in France and Alfred Bucci in Switzerland had independently patented turbo-supercharger designs years before Moss began his work. But Moss had done what earlier inventors could not. He had created a practical, reliable, manufacturable design that could withstand the brutal operating conditions of military aviation. His genius lay not just in understanding thermodynamics and fluid mechanics, but in applying that understanding to solve real-world engineering problems with materials and manufacturing techniques available in his era: the cooling system that protected turbine wheels from thermal destruction, the wastegate controls that prevented overboost, the intercooler designs that reduced compressed air temperature before it entered cylinders, the mounting configurations that integrated turbo-superchargers into aircraft nacelles without creating excessive drag, the production methods that allowed GE and Ford to manufacture hundreds of thousands of units with consistent quality. Every one of these elements required careful engineering work, testing, refinement, and sometimes painful failures before success was achieved. Moss and his teams at General Electric had done that work through the 1920s and 1930s, so that when war came and America needed turbo-supercharged aircraft in massive quantities, the technology was ready. The B-29 Superfortress, which entered service in 1944 and became the primary strategic bomber against Japan in the war's final year, represented turbo-supercharging's ultimate achievement in piston-engine aircraft. Each of the B-29's 4 Wright R-3000, 350 Cyclone engines was equipped with not 1 but 2 General Electric turbo-superchargers, plus 1 mechanical engine-driven supercharger, 3 supercharging stages total. This complex arrangement gave the B-29 the ability to cruise at altitudes above 30,000 feet while carrying bomb loads exceeding 10,000 pounds over ranges exceeding 3,000 miles. The aircraft that dropped atomic bombs on Hiroshima and Nagasaki, ending World War II and ushering in the nuclear age, flew those missions at altitudes made possible by Sanford Moss's turbosuperchargers. The legacy of Moss's work extended far beyond World War II. In the immediate post-war years, turbosuperchargers remained standard equipment on American military aircraft using piston engines. During the Korean War, from 1950 to 1953, turbo-supercharged B-29s flew bombing missions against North Korean and Chinese targets, operating at high altitudes where they were relatively safe from anti-aircraft fire. The technology that had been tested on a Colorado mountaintop in 1918 was still giving American forces tactical and strategic advantages 35 years later. But even as turbo-superchargers reached their peak development in the late 1940s, a new technology was already replacing them. Jet engines, which used gas turbines to generate thrust directly rather than using turbines to compress air for piston engines, offered even better high-altitude performance, with less weight and mechanical complexity. The jet age, beginning with experimental aircraft like the Bell XP-59 Amperes that Moss had helped develop, rapidly transformed military aviation. By the mid-1950s, jet fighters and bombers had largely replaced piston-engine aircraft in frontline service. Turbosuperchargers, the technology that had dominated aerial warfare for 15 years, became obsolete almost overnight as jet propulsion took over. Yet the fundamental principles Moss had pioneered lived on in jet engines. Every modern jet engine is, in essence, a sophisticated application of the same thermodynamic concepts that Moss had explored throughout his career. Hot gases drive turbine wheels at tremendous speeds. Those turbine wheels power compressor stages that squeeze incoming air to high pressures. Fuel burns in the compressed air, producing more hot gases that drive more turbines, creating a self-sustaining cycle. The centrifugal compressor designs Moss had developed for turbosuperchargers influenced the compressor stages in early jet engines. The high-temperature materials and cooling techniques developed for turbo-supercharger turbine wheels enabled the even higher temperatures required in jet engine turbines. General Electric, the company where Moss had spent his entire career, became one of the world's leading jet engine manufacturers, building on expertise gained through decades of turbo-supercharger development. The GE Aviation division that traces its lineage directly to Moss's work in the 1910s and 1920s now produces engines for commercial airliners, military fighters, and transport aircraft used worldwide. When a Boeing 787 Dreamliner takes off powered by GE GenX engines, or when an F-15 Eagle climbs to altitude on the thrust of GE F-110 engines, Moss's pioneering work echoes through the technology enabling those flights. The story of Sanford Moss and the turbo-supercharger is fundamentally a story about seeing possibilities where others saw only limitations. In 1918, when most aviation engineers accepted altitude as an inherent constraint on aircraft performance, Moss looked at the waste heat pouring uselessly out of exhaust pipes and saw potential energy that could be harnessed. When military officials might have accepted that high-altitude flight required massive, complex engines like the Germans were building, Moss proposed a more elegant solution: let the engine's own waste gases provide the compression needed to breathe thin air. The Pikes Peak tests of June 1918 were not just scientific experiments. They were a demonstration that engineering ingenuity could overcome what appeared to be fundamental physical limitations. The thin air at 14,000 feet wasn't an insurmountable barrier. It was a challenge that could be solved with the right combination of thermodynamic principles, mechanical design, and materials science. When the Liberty engine roared to life at the summit and produced 356 horsepower in air so thin that men struggled to breathe, Moss proved that altitude was no longer aviation's master. 26 years later, when formations of B-17 flying fortresses cruised at 25,000 feet above Nazi Germany, their Wright Cyclone engines producing 1,200 horsepower each, despite the thin stratospheric air, they carried Moss's solution into combat. Every bomb dropped from high altitude, every strategic target destroyed, every mission that returned safely because anti-aircraft fire was less effective at extreme altitude, all of it depended on the turbosuperchargers that traced their lineage to that mobile laboratory on a Colorado mountaintop. The bomber crews who flew those missions, 10 men compressed into a cramped aluminum tube at altitudes where the temperature was 40 degrees below zero and where the air was too thin to breathe without supplemental oxygen, probably never thought about turbosuperchargers. They worried about German fighters and flak. They focused on hitting their targets and surviving to return to England. The turbosuperchargers, spinning at tens of thousands of revolutions per minute, compressing thin air back to sea level density, enabling their right cyclone engines to keep producing the power needed to carry them through hostile skies, were invisible to the crews. That invisibility was the mark of Moss's success. The best technology is technology that works so reliably that users never have to think about it. There's a particular irony to Moss's greatest achievement remaining largely invisible, even to those whose lives depended on it. He was a modest, somewhat eccentric engineer who carried pockets of quarters to engage co-workers in coin-matching contests to prove the laws of probability, who claimed that true mechanical engineers wanted to disassemble their pocket watches to understand the inner workings, who hated flying in airplanes despite pioneering technology that made high-altitude flight possible. He published technical papers with titles like The General Electric Turbosupercharger for Airplanes that were read by other engineers but ignored by the general public. He worked for 40 years at one company, solving problems that fascinated him intellectually without apparent concern for fame or recognition. Yet, his work changed in history as profoundly as any general's strategy or any politician's decision. The ability to bomb strategic targets from high altitude helped break Nazi Germany's industrial capacity and shortened World War II, saving countless lives. The fighter aircraft equipped with turbosuperchargers gained air superiority that protected Allied ground forces and enabled the D-Day invasion. The B-29s that ended the war with Japan flew at altitudes made possible by Moss's technology. These were world-changing impacts that flowed directly from one engineer's determination to solve a thermodynamic problem that others had considered too difficult. When Colonel Roger B. Colton, who had been director of Signal Corps Laboratories when the controversial decision was made to develop FM radios for military communications, reflected in 1944 on critical wartime technology decisions, he might have extended his analysis to turbosuperchargers as well. Just as the decision to adopt FM radio technology, despite its complexity, had given American forces decisive communications advantages, the decision to invest in turbosupercharger development, despite skepticism about whether such complex devices could be reliably manufactured and maintained in field conditions, had given American aviation decisive performance advantages. Both decisions required technical courage, the willingness to embrace complex solutions when simpler approaches seemed safer. The B-17 flying fortress that emerged from Boeing's factories, equipped with 4 turbo-supercharged Wright Cyclone engines, producing 1,200 horsepower each, had capabilities that would have been impossible without Moss's work. Service ceiling of 35,600 feet, cruise speed of 182 miles per hour at altitudes above 20,000 feet. The ability to carry 4,000 pounds of bombs on long-range missions deep into enemy territory. Maximum range of 3,750 miles, with reduced bomb load. All of these specifications depended fundamentally on turbo-superchargers, maintaining engine power at altitudes where naturally aspirated engines would have been gasping and dying. Boeing's engineers had designed a superb airframe with excellent flight characteristics, rugged construction, and heavy defensive armament. The Wright Aeronautical Corporation had designed powerful, reliable radial engines. The Norden Company had created a bomb sight accurate enough, at least in theory, to hit specific buildings from high altitude. But none of that would have mattered if the aircraft couldn't fly high enough to stay above the worst of the anti-aircraft fire and operate where German fighters struggled to reach. Turbo-superchargers made high-altitude flight possible, and high-altitude flight made strategic bombing feasible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The technical specifications tell only part of the story. The real measure of the turbosupercharger's impact lies in the operational realities of the strategic bombing campaign over Europe. From August 1942, when the 8th Air Force flew its first combat mission from England, until May 1945, when Germany surrendered, American heavy bombers flew hundreds of thousands of sorties against German and German-occupied targets. Over 12,700 B-17 seconds were built during the war years, and nearly all of them were committed to high-altitude bombing over Europe. Each one flew with 4 General Electric turbosuperchargers, each turbosupercharger representing Sanford Moss's solution to the altitude problem that had limited aviation since the Wright brothers first flew at Kitty Hawk. The losses were terrible. Over 4,500 B-17 seconds were lost in combat during World War II. Tens of thousands of airmen were killed, wounded, or captured. The strategic bombing campaign was extraordinarily costly in lives and aircraft, and historians continue to debate whether the results justified the casualties. But the crews who flew those missions knew one thing with absolute certainty. They knew that flying at 25,000 feet was safer than flying at 15,000 feet. They knew that every 1,000 feet of altitude they gained meant fewer anti-aircraft shells could reach them accurately, and fewer fighters could intercept them effectively. They knew that their survival depended on staying as high as their aircraft could fly while still carrying meaningful bomb loads. Turbosuperchargers made that possible. They were the invisible enabler, the technology that no one celebrated but everyone depended on. When ground crews performed pre-flight checks on B-17 seconds at airfields across England, they checked turbosupercharger operation as carefully as they checked engines, control surfaces, and weapon systems. When pilots climbed toward operational altitude, they monitored manifold pressure gauges and adjusted turbosupercharger controls to maintain optimal boost. When formations assembled at altitude before heading toward their targets over Germany, the turbosuperchargers on hundreds of engines were screaming at tens of thousands of RPM, compressing thin stratospheric air back to pressures that allowed Wright Cyclone engines to produce the power needed for the mission ahead. None of this was guaranteed. Every technological advantage could have been lost to poor execution, insufficient resources, or bad decisions. If General Electric hadn't maintained its turbosupercharger expertise through the lean years between World War I and World War II, the technology might not have been ready when it was needed. If the Army Air Corps hadn't had the foresight to order large quantities of turbosuperchargers in 1937, before war seemed imminent, production capacity might not have been adequate when war came. If Moss hadn't been brought back from retirement to advise on wartime production, quality problems might have compromised the turbosupercharger's legendary reliability. But the decisions were made correctly, the resources were committed, and the execution was excellent. American industry, often criticized for being too focused on quarterly profits and short-term thinking, demonstrated that when national survival was at stake, it could produce complex, sophisticated technology at scales that astounded the world. 300,000 turbosuperchargers manufactured during World War II, each one a precision device requiring high-temperature alloys, careful machining, and rigorous quality control. Ford Motor Company, better known for mass-producing automobiles than for manufacturing aircraft accessories, retooled factories and trained workers to build turbosuperchargers to General Electric's exacting specifications. The production achievement paralleled the engineering achievement that had made it possible. The monument that James Doolittle placed atop Pikes Peak in 1953 stands as a physical reminder of where the turbosupercharger story began. Visitors who drive the Pikes Peak Highway today, now a paved road far more comfortable than the rough track Moss and his team navigated in 1918, can stop at the summit and read the inscription commemorating the tests that changed aviation history. Few probably understand the full significance of what happened there. Most are focused on the spectacular views, the thin air that leaves them breathless, the achievement of reaching one of Colorado's most famous 14,000-foot peaks. But on that windswept summit, where the air is so thin that every breath feels inadequate, where visitors from sea level struggled to walk without gasping, Sanford Moss proved that human ingenuity could overcome natural limitations that seemed absolute. He proved that engineering was not just about accepting constraints, but about finding elegant solutions to problems that others considered insoluble. And he proved that one person's determined effort to solve a difficult technical problem could ultimately change the course of human history. The turbosupercharger that Moss demonstrated on Pikes Peak in June 1918 was not the final answer to high-altitude flight. Jet engines would eventually prove superior for most applications. But for a critical quarter-century, from the early 1920s through the end of World War II, turbosuperchargers were the technology that enabled aircraft to climb where the air was thin and cold and hostile to combustion. They gave military aviation the altitude advantage that shaped aerial warfare throughout the most destructive conflict in human history. They helped defeat fascism by enabling the strategic bombing campaign that crippled Nazi Germany's war-making capacity. And it all began with one engineer, standing on a Colorado mountaintop in the thin air and bright sunshine of a September morning in 1918, watching his turbosupercharger restore power to an engine that should have been choking on air too thin to support combustion, and knowing that he had just solved one of aviation's fundamental problems. That moment, largely forgotten by history, was as significant to the outcome of World War II as many battles that are remembered and celebrated. Sanford Moss gave American aviation the altitude advantage, and that advantage helped win the war that saved the world. And it all began with one engineer, standing on a Colorado mountaintop in the thin air and bright sunshine of a September morning in 1918, watching his turbosupercharger restore power to an engine that should have been choking on air too thin to support combustion, and knowing that he had just solved one of aviation's fundamental problems. That moment, largely forgotten by history, was as significant to the outcome of World War II as many battles that are remembered and celebrated. Sanford Moss gave American aviation the altitude advantage, and that advantage helped win the war that saved the world. Thank you for watching. If you enjoyed this deep dive into the untold story of how one engineer's innovation changed the course of World War II, please subscribe to the channel and hit the notification bell so you never miss another story. Check out the other videos on your screen now for more forgotten tales from history that shaped our world. And let us know in the comments what other World War II technologies would you like us to explore. We'll see you in the next one.